So I wanted to make a lecture about adding and subtracting vectors, and once again we're going to go from that 2D motion intro note guide that we worked on last time, and this time we're just going to move down to this part right here, which I think says 1-1 on it, and I think this should be page 3 in your note guide. And we'll start by labeling what a scalar and a vector are. And we kind of talked about this before. A scalar is something that has magnitude and doesn't point in three-dimensional space. Whereas a vector, let's give an example of a scalar. A scalar would be the number of pages of a book. Temperature. The weight or mass, well, I shouldn't say weight, the mass of something. Because weight is technically a force which has a direction. Something, its mass. So temperature has a direction, right? But let me fix that word. Temperature has a direction, right? But it doesn't point in three-dimensional space. So you can have positive or negative temperature, but it doesn't point. You would never say 40 degrees Fahrenheit to the east, right? That wouldn't make sense. So when something just has an amount, it's a scalar, and it doesn't have a direction. So distance is a scalar. Time is a scalar. And yeah. All right. So energy. Energy could be positive or negative, but once again, that just means whether you gained or lost energy. So you can't just use the fact, you can't just say scalars are always positive, because we're seeing here that things like temperature and energy are scalars, but they also can be positive or negative. And I think sometimes students think, well, that's what makes it a vector, is if it can be negative, and that's not necessarily true. So vectors can be positive or negative. That is true. I'll write that right here. But when we say that, the sign indicates direction. So what is a definition of a vector? I guess a definition here would be something that has magnitude and direction. And points in three-dimensional space. Meaning you could say 40 miles per hour south, right? Go ahead and draw a line here just to split this up. Okay, so so a vector, once again, is something that has magnitude and direction and points in three-dimensional space, whereas a scalar is something that has magnitude and doesn't point in three-dimensional space. we're also seeing that scalars, like vectors, can be positive or negative sometimes, but they don't point in three-dimensional space. So what are some examples of things that point in three-dimensional space that are vectors? This would be things like, they actually occur quite a bit in this class: velocity, displacement, acceleration, things we haven't talked about: force, momentum. All right. And there's more than that, but at least we're getting some of these, right? Okay, so let's go ahead and answer this next one. It says for number 3, you can draw a blank over a vector quantity to distinguish it from a scalar. And this is a vector hat or an arrow. So let me... okay, so we have a vector hat or arrow will look like this. So if I draw a displacement and to indicate it's a vector, I put a little hat over the top of it. If I draw a velocity to indicate a vector, I put a little hat over the top of it. And the same with acceleration or force or momentum, and you get the idea. Okay, so it's just a small way to indicate whether or not something is a vector. Okay. So something you want to keep in mind, and this is what number 4 gets at, that when you draw vectors, you want to make sure that that the magnitude is proportional to the size of the vector that you draw. And this shows up sometimes on the AP test where they will say, draw the vectors with the correct magnitude, or they will give you, because they want to see that you understand that the size of the vector is proportional to its magnitude. So for instance, if this vector represented the velocity 4 meters per second to the right or east, if east is right, then a vector that was, say, 2 meters per second would be half of this. Or by that same logic, a vector that was 8 meters per second would be double. Now, I'm not always going to do this, but I'm going to try to. So when I can, I will draw my vectors so that their length indicates their magnitude as much as possible. All right. So I'll just write that down. Whoops. Let me erase that. Let's write that somewhere. So we'll say right here, draw the length of the arrow, which we're going to call a vector, right? It's an arrow. Draw the length of the vector, which is an arrow, right? Just put that in parentheses. Kind of running out of room here. Let's see if I can draw the length of the vector or arrow proportional to its magnitude. Magnitude is just another word for size, the amount. So if a longer vector indicates a larger vector, a smaller vector indicates a smaller magnitude, right? Okay, so that's kind of what we're saying there. Let me go ahead and separate this a little bit. So we're trying to keep this a little more organized. And I totally understand if you're like, man, I need a separate sheet of paper because this is already too much for this no guide. And once again, I wrote this a long time ago, so it's not perfect, and I'm just making it better as I go right now. Number 5, to add vectors, you must have what two things? So they have to be the same quality. So meaning, and they have to have the same units. This is where I'm kind of short room. Let me, by quality, I mean that you have to add velocity with velocity. So let me, where can I just draw an arrow here? So by quality, we're saying that you can't add, say, velocity to acceleration. And furthermore, for units, they have to match.
Students and staff, this is a drill. This is a lockdown drill. Please lock your doors, and you may continue teaching. Thank you.
They have to match. Okay. Let me go ahead and lock the door really quick. What is the sum of two vectors called? It is called a resultant. And we represent that by a capital R. So go ahead and jot that down. We are not going to do number 7, so I can just go ahead and find some room down here for number 6. So the sum of two vectors is called the resultant vector. I usually like to represent it with a symbol like this, capital R, put a little hat over it, something like that. We'll see that here in a second below when we do some examples. Okay, so I think we're good there. All right, let's move on. Example for number 8, add vector A to vector C. Use the vectors below. Now, when you add vectors, you can pick them up and move them however you like. And when we add vectors, we add them head to tail. So I think, going to get another page here because I want a little more room to explain this. So when I have two vectors, so let me just write this up here. Rules for adding vectors. Add vectors head to tail. A vector, which we said is an arrow, has a head to it, which is where the arrow is, and the part where the arrow isn't is the tail. When we do this, you can pick the vectors up. And move them to place them head to tail. And that's what you want to do. So you pick them up, move them, place them head to tail. All right. What else did I want to say here? All right. So when you do that, right? So I think maybe doing the example will make the most sense. So if we have vectors A and C, I'll come up here and redraw them. We'll have vector A be blue. And we'll have vector C be bright green. All right, so I'm gonna pick up these vectors. I think A was pointed straight up, just like that. I'll label it. Can you put a hat over A? Yeah, if you want to, but you don't have to. So I'm not gonna do it right now, just because I don't want it to look any more complicated than it needs to be. So I have vectors A and C.
This concludes the drill. Thank you.
All right, so I can then pick those vectors up and put them head to tail. So I know, and so let's go ahead and do that, right? Let's pick vector C up, the green vector, and place it right here so that it is head to tail with vector A. And let me point that out. So we have the tail of vector C near the head of vector A. Once you've done this, you're almost there, right? You're almost ready to draw the resultant, but you have to know how to draw the resultant. What you have here is kind of like a scavenger hunt, right? Meaning you have now a path. You're going to walk up, then you're going to walk right. So if we were following this path, we would call this point right here the start of the path, right? And we would call this point right here the end of the path. And what we do to draw the resultant is we draw a line. I'm going to draw a dotted line in this case so you can see how it's different. That goes from start to end. And that is your resultant. And let me say that again. You draw a line from start to end that points from start to end. So the vector R points from start to end. All right, I got to start a class here, so I'm going to have to pause it, but let's add that last rule. So draw vector R, or the resultant, right? So that it points, so that it points start to end of the scavenger hunt, right? Of the scavenger hunt. You know, it's like a map, right? I don't know, you get the idea. So draw your vector R so that it points start to end. Okay, so we will we'll go ahead and pause it there, and then we'll come back and do some more examples of adding vectors and then look at subtracting. All right, so let's do a few more examples before we move on to subtracting vectors. And so we got a couple down here at the bottom of this page. Numbers 10 and 11, they're both just vector addition. And I'll go ahead and use some colors just to make it easier. We'll call vector A this blue vector in both cases, although it's going to be different than the one below. Vector C will be this purple vector. All right, so we have something like this, right? All right, so let's do 11 first because I think it's even easier. So when we add A to C, we're just going to pick one of these vectors up and put it head to tail with the other. I think it's easy just to pick A up and move it so it's head to tail with C. It's just like that. C is about double the magnitude. So we have something like that. We then find the start. If this is like a scavenger hunt or a treasure map, this would be the start. This would be the end. And so our resultant is going to go from start to end. I'll just go ahead and pick a different color here. I don't know, pick orange or something. So I'm going to go ahead and draw a dotted line. I don't have to use a dotted line, but here I just like to. So there's R right there. So A plus C is equal to R. And I could write that in vector hat notation. I could say vector A plus vector C is equal to vector R, right? And there we go. Now, if A and C instead, so if A instead pointed to the left, what would happen now? Well, let's again pick up A and move it so it's head to tail with C. So I'm going to redraw it just because I think it might be easier to see. All right, so I'm going to pick up vector A and place it head to tail. And when I do that, it's going to be right there, right? Now we can see the tail of blue, or A, is near the head of C, which is purple. Now if I walked this like a treasure map, right, where would I start? Well, I'd probably start right here, right? Then I'd follow the purple vector to the right, and then I'd come back with the blue vector and end right here. Now, although it's kind of hard to see this, the vectors are on top of one another. I usually offset them a little bit just so it's easier to see, but they are right on top of one another. So what we can see then is we just once again go from start to end. Let me get that orange. All right. From start to end, right there is what's left over. So it's really like A just canceled off a part of C, and we're left with R here in orange, which is just a piece of C, right? A piece of the purple vector, and it still points right. All right, good. So hopefully there's no questions there. Just a little practice. We won't do this one on the bottom of the page. We don't need it. And let's look at the practice. So I think I'm going to hand out some practice in class. And here's the vector addition practice right here. Here's the back of the addition page. And this is if I don't hand it out in class, it's on Schoology. Let's look at this example number 12. I like this one because we're adding 3 vectors. And does that change anything, right? So let's make E blue. Let's make, I guess I could use a highlighter here, but oh well. Let's make F orange. Let's make G green. Okay, so we have these 3 vectors that we need to add together. So once again, we need to put them head to tail, right? So probably need a little bit of room here, but I think I could have room up above here. So I'm just gonna pick these up and put them head to tail. So I'll go ahead and put vector E here. Does order matter? That's a good question. We should probably take a look at that, right? Let me get a separate piece of paper then, because I think that will help. So let me add a page here. All right. So does order matter is also a question worth answering. So we have vector E. We're going to put it head to tail with vector F. So we'll just move F right here. We're then going to put that head to tail with vector G. So notice it's just head to tail, head to tail, head to tail. All right. And then our resultant is going to point from start to end. We'll call that R. All right, what if I would have did a different order, right? What if I would have did F plus G plus E? Or F plus E plus G? Let's do that. So what I'm saying is, what if instead I would have did F plus E plus G? All right, well, then I'll start by drawing F. I'll then put E next, head to tail with F. So it's going to look like this. And then I'll put G. My drawing's not quite perfect, but you can see here would be the start, right? Here would be the end. And so let me draw that again. So there's start and there's end. And then, whoops, dang. Get this out of here. So we can see that it's roughly, you know, my drawing's kind of crummy and kind of not perfect, but it's roughly the same. Check that out. So does order matter? No. So we could have put those three vectors in any order, head to tail on all of them, and it's going to work out. So make sure that makes sense why they're each head to tail, and if it doesn't, obviously go back and watch that part and make sure that that makes sense to you. All right, so let's go to the next practice here. Subtracting vectors, right? So I got a couple highlighted up there. I actually want to start with the back of the practice on subtracting vectors. And once again, if you don't have this in your note guide. You might have the separate paper on Schoology. If you can just write this down on a separate sheet of paper while you're taking notes, it's fine. All right. So subtracting vectors, what do we do, right? What are the rules here for subtracting vectors? All right, so let's write some rules down. So what we want to do when we're subtracting a vector, so let's say we have a what we're gonna do is we are going to follow the rules for vector addition. But we are going to have to flip the directions on the negative vector. So and the negative vector is the one being subtracted. So what I'm trying to say is this. We're going to use the fact that when you do a subtraction problem, for instance, 4 minus 3, this is the same as saying 4 plus negative 3. So we're going to use that logic right there, right? In either case, the answer is going to be 1. So if we have, for instance, down here, well, we have to understand that what a negative sign means, right? Negative and positive are direction. So if we come back to just our vector A, which maybe before was just this, right? If this is A, then this is negative A, right? Yeah. If this is B, then this would be negative B. So all I have to do is flip the sign on whatever vector is negative, and flip the direction of the arrow, right, to make it the negative vector. If I have a vector that points like this, and this is A, then, or let's give it a different letter, right? We'll call it, I don't know, C. Whoops. call it C. So then this right here, a parallel vector, but just pointed in the other direction, would be negative C. And we're going to use that idea right there. So coming down here to H minus J. All right, so here's H right here. We'll use a different color here. Let's use red. And J is going to be this vector. We'll use black. All right, right here. So we have H minus J. All right, well, let's think about this, right? So what we're saying then is we have H minus J. This is the same as H plus negative J. What the heck is negative J then, right? Well, down here, we can see J points like this. Then that means that this right here pointed in this direction. The same parallel vector pointed in the other direction would be negative J. So if we add H to negative J, that is the same as H minus J. So these two are equal, right? H minus J and H plus negative J. So let's go ahead and add that, right? Let's put H and negative J head to tail. So I'll go ahead and draw H. I'll go ahead and draw negative J head to tail with H. All right, so I think it's going to look something like, I'm not sure if it's going to stretch all the way. All right, something like that. And then this will be my start. Follow the red vector, follow the black vector. This will be my end. So the resultant always points from start to end. Make sure this points. It's got to point. Otherwise, it's not a vector, right? So, and I should use a different color for R. Use orange again. And I should even make sure I go all the way there, right? Because I don't want you thinking I'm just, it is appropriately that magnitude right there. Of about, what, a centimeter or so. All right, so anyways, there we go. That's what we have there. H plus, and we added it to negative J is equal to R. What if, and they do ask us this, let me draw a boundary here. What if we then take a look at question number 15, J minus H. All right, so now this was, the one we just did was number 13. So let's write that down. This is number 13. What if we then take a look at number 15, which says J minus H, which we just said just a second ago for the other one, that this is the same as J plus negative H. Once again, we got to figure out what negative H is. So if H points like this down here, right, in red, then negative H would point parallel, it would be parallel but point in the opposite direction. All right, so if what we're saying then is that to do J minus H, which is what the question is asking, we are just going to take J and add it to negative H. Well, let's look down here what J is. It's this vector right here in black. I'm going to make it blue. It's this vector right here in blue that points to the right. So let's go ahead and add that up here. Let's then add that to negative H. So head to tail with negative H. Negative H is this vector right here, which points down and left. And so let's go ahead and draw that up here. And we're going to put it head to tail with J. Okay, so maybe something like this. And there is negative h right there. Okay, I'm just going to move this letter J just so it doesn't look like the two are crossing paths, because they're really not, right? Okay, so now we look at this like a treasure map. And where would we start? Well, we'd start right here. We then end at this point right here. So our resultant, which I'll do in orange again, is going to go from start to end and be R. Now, a good question is 15 and 13 the same? Is h minus j the same as j minus h? And what we're seeing is the answer is what? Well, let's look at the resultant at the end. In one case, the resultant, which is orange, is, let me see if I can find a decent highlighter for this. I don't think I can. We can see that, I'll just do this. I'll write it in orange. That for 13, R is equal to this vector. Whoops, dang, this highlighter. Is equal to this vector for 13, right? This is R. But for 15, this is R. So are the two the same? No. They have about the same magnitude, sure, which is about a centimeter or so, but they have different directions, so the vectors are different. And there you have it. So it's very similar to adding and subtracting numbers, right? We say when we add that order doesn't matter, right? You can say 4 plus 3 is equal to 3 plus 4. And it's also similar to subtraction, because 4 minus 3, which is equal to 1, does not equal 3 minus 4, which is equal to what? What's 3 minus 4? Negative 1. So we see that it's very similar to subtracting numbers here, that h minus j is not the same as j minus h. Okay, I don't think there was anything else that I had felt like I needed to do. Question 7 here, if we just do one more. Let me add one more page in here. All right, I think I have enough room. All right, question 7 here, a minus c minus d. Let's go ahead and, so we have a up here, obviously. It's already done for us, but what is, this is like us saying, when we say a minus c minus d, we're saying a plus negative c plus negative d, right? And these are vectors, all three of them. So when we do this, we need to, when we add these three vectors, right, which is what we want to do, we need to know negative c and negative d. And when we add things, order doesn't matter. So once we've flipped those to the negative sign, now the order doesn't matter. So when we add three vectors, the order still doesn't matter. 2 vectors, 4 vectors, whatever, it doesn't matter. Just add them all up. All right, so a minus c minus d. Okay, well, here is minus c. Let's see, c points to the left, so minus c would point to the right. And d points straight down, so minus d, or negative d, would be straight up. And that's kind of cool to see, because here we're seeing negative d has a negative sign but points up. And so negative is just the opposite of whatever d is. Since d is down, negative is up. And so since down is positive, negative is up. All right. Okay, so let's go, let's solve this problem then, right? I should have picked a different color for negative d. Let's pick, I don't know, let's pick green. All right, there we go. Negative d is this green vector. So we're going to add a, negative c, and negative d. So what's that going to look like? It's going to look like, this is where I definitely want just a tiny more room. Let's put it right there. Okay, So, all right, let's go ahead and write these. A is going to be about, what, 1.5 inches or 2 inches. They're all about the same magnitude, A, C, and D. So we have this, right? So we have A. We have negative C, head to tail with it. And then we have, I already passed it, yeah, I did. We have negative D pointed like this. Okay, so then we just follow the map, right? Follow the treasure map. Here's the start. We're gonna go right, right, and then up. Here's the end. And then R is the orange dotted line. R always points from the start to the end. Okay, and that's it. So hopefully this is making sense. Adding and subtracting vectors, we will use it throughout the course, and when we resolve vectors especially. And hopefully this is making sense, and we did some examples there. So yeah, hopefully that's good. All right, so subtracting vectors, follow the same rules as vector addition, but change direction of the negative vector, which is because we're going to add a negative, and that's the same as subtracting. And hopefully you remember that from this right here from math class, right? That 4 minus 3 is the same as 4 plus negative 3, and we're utilizing that fact as well. Okay, that's all for the lecture. Have a good day.